Welcome back. So the topic of this lesson now will be to specifically talk about how to find the sum of a finite and an infinite geometric series. Let's redefine or remind ourselves what a geometric series is. In a geometric series, we can start the series with any number we wish, and then to generate the rest of the numbers, we just have to multiply successfully by the same number each time. That number will be called the common ratio. Let's just give an example of that. Suppose maybe I just want to start my series with the number 2. And then to make every number after that, I will just multiply the previous number by, let's say, 5. And so I'm going to actually write it out without actually finding the explicit numbers. I'm just going to show you that I'm multiplying by 5 every time. And so 2 times 5 would be the second term. 2 times 5 times 5, or 2 times 5 squared, would be the third, and so on. I'm going to write about 4 or 5 of them down here. Kind of like this. And I could put this in the sigma notation. If you notice that my first term was 2, basically every term is 2 times the power of 5. It's just we have to make sure that it starts literally with 2, or you could think of this as 2 times 5 to the 0. So if our index of the sum starts at 1, we need to back off 1 from the power of 5 so that I start with just a 2 or whatever that first number is. So I would write mine like this, and then here's the general idea for any geometric series. And you'll have to ignore the fact here that this should be n equals for both or I for both. So let me just change this to n here. So those match. Okay, I used I up here. The goal of this lesson is to find a way to quickly sum together terms of a series like this. We'll first start with a finite series, which means we'll start with an initial number and pre-decide how many of these numbers we like to add together. And then so find what's called that partial sum. We talked about that in the last video. Partial sum would mean to find a sum of a finite number of numbers. And we'll try and take that and merge over to talking about an infinite sum. So what I'd like to do here is just actually take a specific example of a geometric series and find its sum not by adding them up one by one by one, but finding a clever way to rearrange them so that I could use this idea for much longer sums. So you might not see it as necessary to add up 5 of these numbers, but you hopefully would find it beneficial if I had to add up 105 of these numbers. So let's take the series I was writing a minute ago. I'm going to start the series with the number 2. Typically we call that number A. And we're going to make this geometric series by using a common ratio of 5. And so in summation notation, I'll use n this time. And we're going to write the general term 2 times 5 to the n minus 1. And let's just say we wanted to add up, I don't know, 5 of these numbers. You know what, let's not use 5. I don't want to use it twice here. Let's just add up 4 of these numbers. So we're going to add up the first 4 terms, which would be, I would call that S sub 4. It's the partial sum of 4 using the first 4 terms. And so I'm going to start by just listing them out. 2 times 5, 2 times 5 squared, and 2 times 5 cubed. There's my 4 numbers. Now we could, of course, pretty easily grab a calculator and add those 4 together. What I like to do, though, is demonstrate that I can do this in a different way, so a way that I could use to quickly add up even 104 of these numbers. So watch what I'm going to do. I'm going to, underneath here, I'm going to multiply every number on both sides of the equal sign by the negative of 5. So on this side, I'm going to call that negative 5 times S4. And now what I'm going to do is I'm going to multiply every term in the sum by negative 5. And after doing that, I'm going to write it underneath a like term in the previous list. So for example, the number 2 multiplying by negative 5 is now going to be 2 times negative 5, but I could write it as negative 2 times 5. So I'm going to write it under here. So notice it kind of shifts it to the right here. 2 times 5 would be 10, but now I'm going to multiply that by negative 5. So I'm going to write this as negative 2 times 5 squared. And you see where this is going. So these are just going to shift down a little bit. So there's my third, but I've only got 3 terms so far, so this last term has to shift down to where there was no space before, and it would now be negative 2 times 5 to the 4th. Okay, so now why did we do this? Why did we multiply by minus 5 and write it under there? I think you'll see in a minute how this is actually going to help, especially when there would be a much longer list. I'm now just going to add the columns of like terms. So in the first side, you can think of this as 1 S4 minus 5 S4. So the net total is, those are like terms, negative 4 S4. Now look what happened over here. Look at every column except for the first and last. In the first column now, 2 does not have anything to go with it. But if I combine these, it's just going to be 2. But look what happens in every column after that until I get to the end. For example, 2 times 5 minus 2 times 5. It adds up to 0. It adds up to 0. It adds up to 0. Only the very end now, where there was nothing before, do I have, again, minus 2 times 5 to the 4th. I hope you noticed that this would have happened if I do this way, if I had 5 terms to combine, or if I had 105 terms to combine. It wouldn't have mattered. If I do this way, I noticed also why I picked the multiply by negative 5. 5 is the exact common ratio, so I multiplied by the negative of that. So the goal is to look at the simplest expression here. Here I have 2 minus 5, or minus 2 times 5 to the 4th. Let's notice that 2 is a common factor in there. And I can write the other part as 1 minus 5 to the 4th. And this equals negative 4 S4. To solve for S4, I've got to divide by negative 4. Now, what I'd like to point out here is that there's something special about the negative 4 also, and that it is exactly 1 minus 5, and 5 was the common ratio. So this would happen every time also. So let's actually go back and change this to make it more indicative of what's going to happen every time. So notice now, I have a nice little expression here. Maybe I wouldn't have had to do this type of thing to only add up these 4 numbers, but if I was going to add up 104 of these numbers in the same way, I definitely wouldn't want to have added them all up one by one. This gives me an idea of how I could do it. Notice the role of these numbers. 2 was the number I started with in my series. 5 was the common ratio. And 4 was the number of terms I was adding. And so I think what I can do in general here is say, let's say I wanted to find the sum of any set of numbers in a geometric series. I know I'm going to start with A, which was my 2. Here, 1 minus 5 to the 4th is really 1 minus the ratio raised to the number power that matches the number of numbers I'm adding together. And then I'm dividing by 1 minus the ratio. In fact, this is how you can sum together a geometric series, a finite geometric series. Now, if we were to extend this further, maybe I want to add up forever and ever of a geometric series. So I could start with looking at what we just discovered, that the sum of a finite geometric series is this. This is a finite geometric. In other words, it's a geometric series with a common ratio, and you're told how many numbers in the series to add together. Like maybe find the sum of the first 7 numbers, or the first 10 numbers, or the first 25 numbers. We're going to go and grab this formula right here. But now, let's think about adding and adding and adding forever. Sometimes the geometric series, if added indefinitely, will just keep growing and growing. But there are other times when it won't. And if I look at this formula I made here, you can kind of see why. Remember we talked about in the geometric series or geometric sequences, the terms will shrink to 0 if the common ratio has an absolute value less than 1. So think about that. If the ratio were 1/2 or 1/10, and you raise that to a bigger and bigger exponent in this formula, this part is going to become almost 0, and essentially it's 1 minus 0. And so that leads to leaving only a over 1 minus r left. And that's what we're making note of in this theorem here. If I have a geometric series with a common ratio that is less than 1, or let's say it could be negative, so its absolute value is less than 1, you can add forever and come up with its sum. So let's make a note of that here. It's mentioned up here, but I'm just going to make a note of it here again. So if the absolute value of r is less than 1, you can add forever, and the series will converge. To exactly a, which was the first term in the series, divided by 1 minus the ratio. Sometimes the information you're given is not explicit enough to use this formula. You sometimes will need to write out the first few terms to discover that it is a geometric series and what is the first term and what the common ratio is. But once you know that, we can simply use this to find what the sum converges to. Let's give it a try. Okay, so I've got a series here that I want to decide if it converges or diverges. Let's first decide if it's even a geometric series at all, just by writing out the first few numbers. This one says to start with n equals 1 and take 6 times 2/3 to the n. Well, the first term is going to use n equals 1 and be 6 times 2/3. But then after that, I see I'm just going to be taking that and taking higher powers of 2/3. And so on like this. So I can tell that the common ratio is the 2/3, and because that is less than 1, I know this is going to be a geometric series that converges. So now we just want to know what it converges to. Well, our formula requires we know the very first number, so that's not explicitly written here yet. I need to multiply 6 times 2/3, which would be 12/3, or 4. So the first term is 4. So in other words, using the notion of the previous couple slides, we could have written this series in a little different way by writing it as 4 times 2/3 to the n minus 1, and it would have made the same list. However, now let's just find our infinite sum and say this is going to be a, which is 4, divided by 1 minus the ratio. So 4 divided by 1/3 is 12. I encourage you to give this a try. Try typing this sigma notation into your graphing calculator. And instead of using infinity, which we can't do, try putting in a really large number up here and see if it doesn't get really close to a sum of 12. So that's what we say this series converges to. As we add more and more numbers, the series will continue to grow, but not and get closer and closer to 12. And let's try one more. This time the general terms are not explicitly given, but we are given the first four numbers. So let's see if this is a geometric series first. To go from 9 to -3, if it's a geometric series, we have to figure out what we're multiplying by. It looks like multiplying by -1/3. We'll do it. And if I take from -3 to +1, that's also multiplying by -1/3. And same thing to go from +1 to -1/3. So this is a geometric series. The common ratio is -1/3. And so since the absolute value of r is less than 1, the series will converge. Just a matter of to what. So remember, the first term is 9, and the common ratio is -1/3. So our sum of an infinite geometric series is a over 1 minus r, assuming that the ratio is the right size, and it is. So this one is going to be 9 divided by 1 minus -1/3. So 9 divided by 4/3 ends up being 27 over 4. This series will converge to 27 over 4. I hope this helps today, guys. I'll look forward to seeing you guys back here in a couple of days to expand on this topic further. Have a good day.